So in these documents, they give you a lot of examples on what these different variations would look like, especially if you look at this one here, which is L2VPN interworking. They pretty much show the syntax format for all of these different variations. Okay, so how to configure L2VPN between, let's see, there should be examples towards the bottom, which is this. Frame relay to Ethernet, okay, or let's say Ethernet to, I want to see if it has L2TPv3, which is basically just this difference, what the encapsulation is. So if we look at their example, let's say Ethernet to anything. Using bridged interworking. Well, we're not going to use interworking anyway, so let's just look at this, which would be, let's see, this is the legacy syntax. Okay, so it shows the legacy syntax, and then the next one, using the commands associated with the L2VPN protocol-based CLI, which is the new standardized version of it. So it would be something like this. Okay, this is kind of a bad example because this is using legacy frame relay, but what it would look like in terms of the L2TPv3 would be this. So we already have our pseudo-wire class, which is using the, and actually let me just build this live on the CLI, is we already have the pseudo-wire class that is doing the setting what the encapsulation is. So let's do this on router 4. Let's say default interface gig 2, and same thing on router 5, default interface gig 2. Okay, the end result should be that routers 7 and 8, which are the customers, they're going to lose connectivity to each other. Okay, ping 10.0.0.8. Okay, those guys are in the same segment. Okay, what we're now going to do is to say when traffic comes in the interface, I don't care what the encapsulation is. So I'm going to take all VLANs and I'm going to put those in an X connect that goes across to the other remote peer, but the encapsulation is going to be L2TPv3. So the way that we're doing this is with the L2VPN cross connect. So globally, we're going to say first on the physical port that we have a service instance. Okay, service instance would be, where does it show it on the other side? Which would be, well, let me just let's look at the AToM config, because that's a little bit easier to read, because this is the legacy stuff. So we want, probably this one. Where's the physical Ethernet? Which is, now this is using a different format too, which is the interface pseudo-wire, which again, this makes it overly confusing because there's so many different formats for the syntax. But let me basically build this from scratch. What it would look like is something like this. At the port level, we specify what is the service instance. Okay, the number itself is any locally significant number. It relates just to this local router. Okay, so let's say for simplicity, service instance is 1. And it's for Ethernet. Okay, then we say what type of traffic are we trying to match as it comes in. So we're going to say what's the encapsulation. Is it untagged traffic, which would be the native VLAN? Is it a particular .1Q tag? So is it VLAN 10? Is it .1P tagged, which would be like your IP phone call, for example? Or if we were to just say all traffic would be encapsulation default. Okay, so I don't care what traffic comes in from the customer. Any Ethernet frame is now going to be part of this service instance. Okay, then we're going to create the L2VPN globally with the L2VPN cross connect. We give it a name. We'll say that this is L2TPv3. And we say that the member is going to be the gig interface, which is gig 2. And then what particular service instance on that port, which in this case is service instance 1. Okay, so again, the point of this being is that the service instance 1 is saying all traffic that comes in. So it's every Ethernet frame regardless of what the VLAN is. So we're putting it as part of the cross connect. This is essentially the local attachment circuit. And then we specify what's the remote one. Okay, the remote one is going to be the member. And the member's address is 5555. And the encapsulation, okay, the virtual circuit ID, let's say number 2, And then the encapsulation is going to be, this one only supports MPLS. So let's say that the, let's call a template and see if we can call L2TPv3 from this, which is, we then say the template type is a pseudowire template, L2TPv3, and the encapsulation is L2TPv3. No local interface set. We need to set the IP local interface. Okay, it's going to be the loopback and then the encapsulation. Okay, so then back under the XConnect, if we show run section XConnect, let's see if it gives an error when we specify the template now. Okay, so let's look at this full config and then basically move it over to router 5 as well, which is, starting at the top here, we have the pseudowire template type pseudowire. We then have the XConnect. Actually, no, first we have the service instance. Okay, so that's going to be on the quote-unquote physical port. We have the XConnect that is calling the service instance on the port, and then also calling the remote neighbor, and then the pseudowire template. Okay, so basically the only thing that's different between these two configs is just the target IP address between them. So on router 5, go ahead and apply this. Okay, now from the customer edge point of view, if we now go to ping over the tunnel, let's look at the show L2VPN says the attachment circuit is up. Inner working is none. Let's check if it says that also on router 5. Session ID. So they should agree on, okay, they both say the tunnel is up, segment 2 is up, segment 1 is up. Okay, physical port is up. Show IP interface brief. Physical port is up. Let's look at on the, from the packet capture, let's see if this is actually being encapsulated or not. You'll see sometimes with the virtualization that the layer 2 VPN implementation is a little bit finicky. You can run into a case where you have the correct config, but it's not bridging the traffic. Sometimes flapping the port will help. Sometimes you have to reboot the box in order to get it to actually work. But the CSR 1000Vs are supposed to support this in production. So they're actually meant to bridge the data plane. So let's say is the IP.source is equal to 4444. So here's the control message. So it is tunneling over to it, but it's not encapsulating. Okay, let's try this. Let me change the encapsulation to MPLS to see if it'll encapsulate over the MPLS core. So let's look at the show run. And I would need to change the pseudowire template. Okay, and I don't know if it's actually going to let me change this while it's currently up. Let's say the encap is MPLS. Cannot change on an existing template. Okay, so let me simplify this one point. If we show run pipe section cross connect or XConnect, we can set the, instead of calling the template, we can just call the encapsulation right there, which would be the member has an encap of MPLS. Okay, basically you only need the template if you want to create the other options, but from the minimum config, you just say we're doing encap MPLS. Okay, so same thing on the other side. On router 4, let's show run pipe section XConnect. And what we should see happen if this is going to work is that the two boxes are going to form a targeted LDP session. Okay, the LDP session is going to be to advertise what the MPLS label is that we're going to use for the L2 VPN. So if we show MPLS LDP neighbors, neighbor is up. Okay, if we look at the neighbor for router 5, the difference between it and one that's on a directly connected port is that the ones that are connected, we discovered them by sending the UDP multicast to the all routers, the 224.0.0.2. But in this case here, since we already specified manually what the endpoints of the layer 2 tunnel are, router 4 knows to send the TCP message directly over to router 5. So if we now look at the show MPLS forwarding table, we now have a label that's going to be associated with a layer 2 circuit. So basically it says that if I receive traffic in with label number 26, I know that it's supposed to go out this interface, and I'm going to remove the entire label stack and just send whatever the payload is underneath there. Okay, so now if this works, we can see now 7 and 8 have transport to each other. So if we ping, let's say we ping the broadcast address, we can see that we're getting reachability between them. But if we look at this from a packet capture point of view, the difference should be between this and the L2TP tunnel is that this one is going to be directly MPLS encapsulated. So ping to 10.0.0.8, let's say repeats 100 packets. And if we look back at the capture, this should be directly, we should be seeing, let's say ICMP. We have these packets that are coming from 7 directly to 8. Okay, if we look in the payload here, the difference between them is now we have our outer Ethernet header. Okay, the outer Ethernet header in this case is the one that went from 4 to 6 and from 6 to 5, so it's in the core of the network. And then the next header in the stack is MPLS. But notice that there's 2 labels. The top one here, this is our transport label. Okay, transport label, which is generated by LDP, by traffic engineering, by BGP, whatever we have running in the core that's getting us reachability between the loopback of 4 over to the loopback of 5. Then in the middle, below them, we have the VPN label. Okay, the VPN label is also referred to here as the pseudowire label. It's basically the L2 VPN label as opposed to L3. This one is derived from label distribution protocol, again, because we have a point-to-point targeted LDP session going between router 4 and router 5. Then the payload is Ethernet directly encapsulated in MPLS. So where in the previous example with L2TPv3, we had Ethernet in IP, and then IP was in MPLS in the transport core, but that MPLS label wasn't really needed for the transport of the L2 tunnel. Okay, then in Ethernet, we have whatever the rest of the payload is. In this case, it's the ICMP ping that's going between them. Now, this likewise does have a legacy equivalent of the syntax, which we could likewise just go directly to the port and say we want to do an XConnect to, and actually it doesn't let me do the XConnect now because there's a service instance that's applied on the interface. Show run interface gig 2. But if this interface did not have a service instance, we could simply say XConnect, the address like 5555, whatever is the circuit ID that we want to use, like circuit number 3, and then the encapsulation would be MPLS as opposed to it being L2TPv3. So again, from a configuration point of view, they're very, very similar to each other. The difference really is in the core of the network, do I need to tunnel the traffic over regular IP, or can I tunnel it over MPLS? If it's tunneled over MPLS, you can use either L2TPv3 or MPLS, okay, or AToM. If it's only IP native, then you would have to encapsulate it as L2TPv3 or add an intermediate header like GRE, and then GRE you can put MPLS inside. Which again, we'll look at that in later examples when we look at like the point-to-point versus multi-point GRE, and then running MPLS either L2 VPN or L3 VPN inside of there. Okay, the verification of the new syntax format here is going to be the show L2 VPN. So let's see if they show this here, which is the, let's say show L2 VPN. Show L2 VPN AToM binding. What I am looking for is the show L2 VPN virtual, no, show L2 VPN. Let me think, what is the command that I'm looking for here? It is, show MPLS, it's an MPLS command. Show MPLS L2 transport, virtual circuit. Okay, this shows that the local interface where encapsulating traffic as it comes in gig 2, and then it's going out to the destination of 5555. This verification here we'll see is the same between AToM and VPLS. The difference being is that AToM is point-to-point, and we do not need to do any MAC address learning. So there's not a bridge group, and there's not a virtual forwarding interface that is associated with the AToM cross-connect. If we look at the show MPLS L2 transport VC detail, this shows the specific negotiated values over the circuit. So some of the things that would be important are what are the MTU of the physical port. If one side is using jumbo MTU and the other side is not, then the X connect will not come up. This is part of the negotiation of it. We can also see what is the pseudo-wire label or the VPN label that we're using between these. And when we look at the packet capture, this is the one that's going in the bottom of the stack. In this case, label number 26 was the one that we negotiated here as the VPN label. Okay, this is the same equivalent of saying show BGP VPN v4 unicast, and look at what is the L3 VPN label that is exchanged between the PEs. The other output that you would be looking for here is that the targeted hello is up, because if there's some sort of transport problem with LDP, and you can't exchange the label, then the pseudo wire itself is not going to come up. Okay, it should say that the virtual circuit is up, and then also the attachment circuit, which in this case is the Ethernet interface, and then the service instance, which is number 1 that I had defined on the port. But otherwise, if we had done this with the legacy syntax, which is just doing the X connect directly on there, it would just say the attachment circuit is gig or Ethernet 1, or gig 2 in this case actually, as opposed to the service instance on the port. But the advantage of doing it with the new format is that if you wanted to come back later and add an additional X connect, you could create that on a different service instance, and you can also do translation between them. So the translations between them, you'll see that this does get pretty complicated in terms of what are the different variations you can do. And where this is documented, it's called an Ethernet virtual connection or an Ethernet virtual circuit, an EVC. So with an EVC, if we look back at the example where it shows the L2 protocol-based CLI, that's where under the service instance, it shows, do I want to change the tag values as I'm coming in or going out the link? Okay, and the example that we did in the workbook here, we put together a long list of talking about what are these different variations and what's the end result in the encapsulation. Normally, this use case is in Metro Ethernet. When you want to do some sort of VLAN translation or some sort of Q-in-Q tag, when you're sending the traffic over either the native Ethernet network outside of MPLS or with Ethernet over MPLS. So I'm not going to go over all the variations now because it does get really, really involved. But if you look at the SP workbook, and under Layer 2 VPN, this is point-to-point service using the Ethernet virtual circuit, which is basically what we did here. Which is point-to-point using the EVC. So this is defining, again, the service instance on the port level. And then, in this case, the X connect is directly under the interface. But in my case, I did it separately in a global X connect that's calling the service instance. Effectively, they're doing the same thing. Mainly, the point of the new syntax is to make it more modular and to unify the syntax across multiple platforms. Where down here towards the bottom, this is what I'm talking about. Okay, so if you say encapsulation.1q20, Hopefully self-explanatory. It means match tag 20. You could also say a range, or so a consecutive range, or like a comma separated value. So match what are these specific tags, and then you say what do you want to do to them. Okay, so you can say match the first tag of 20 in the inner tag of 10, or the first tag of 20, the inner tag of 20 to 40, and then do you want to match based on the class of service value? So you can get really, really granular in terms of the classification of how the traffic is coming in from the customer attachment, and then you can also modify the frames. So this says rewrite ingress tag pop1 symmetric means remove the outermost VLAN tag. Okay, if you say pop2 symmetric, it means both inbound and outbound, you're popping both tags. You can then say I want to also push a tag onto it, so to add VLAN 100. You can push multiple tags, you can do a translation between them. So again, you can get really, really granular with the classification here, but where you would find this in the documentation is under the Metro Ethernet switches, like the ME3800. So from the main documentation page, if we go to switches, then service provider Ethernet access, let's say ME3600X, config guides, configuring Ethernet virtual connections, EVCs. So basically this is the same type of logic as the MPLS layer 2 VPN, but you can do it outside of the scope of MPLS. That you're using, as opposed to an MPLS transport label, you're using an outer VLAN tag as basically the Metro VLAN tag. So it means that the boxes don't necessarily need to be MPLS aware, but you can have the end same result where you're basically tunneling the traffic over Ethernet as opposed to tunneling the traffic over MPLS. Okay, so let's recap the config of this real quick. Let's say show run pipe section xconnect. And then at the interface here, this actually should say, now the xconnect should say like MPLS. But we're basically saying match traffic on gig 2 as it comes in service instance 1. Service instance 1 is saying all Ethernet traffic, so we're not looking at a specific .1Q tag. We're then connecting it remotely to this IP address. We're negotiating a virtual circuit number, and we're using MPLS as the encapsulation. So then we looked at the show MPLS L2 transport virtual circuit summary. Or actually it just might be L2 transport summary. Okay, this says that the circuit is up. Okay, it's going over to router 5. And if we show MPLS L2 transport VC, that shows the actual circuit, and then the VC detail is going to show the details of what was actually negotiated. Okay, and as someone had asked a question here, is the only way to see the out labeled to the other tunnel is under the transport? I think there are other ways, but the problem is it doesn't show it under MPLS, show MPLS forwarding table. It does show you what the local label is. So this is the one that I advertised to the other end. But the problem is you would have to know which particular circuit is this xconnect actually going to, which that doesn't tell you here. So if we look at router 5 and look at the show MPLS forwarding table, it says my local label out to them is 26. Their local label back to me is 26. In this case, it's just coincidental that they have the same number of labels. But it means that bidirectionally, when 4 sends traffic to 5, it's going to use number 26, and then vice versa, the other direction.